that Adrian is going to explain that to us very, very nicely. Adrian, whenever you want.
Yeah, thanks, Javier. Also want to thank Jane for switching the talk with me, the slot. So let me start with some comment about what I'm going to present. So most of the content that I'm going to show in this talk, you can find it in this paper. So if you want to look into more of the details or the examples that I'm going to show, you can just scan that code and that will take you to the archived version of the paper. So mostly what I'm going to give here is mostly an overview of the ideas that are in the paper. I also want to acknowledge Gonzalo Arranz. He's my postdoc. He also worked on this. And I want to acknowledge the NSF, that this is funded by the NSF. So the motivation, this is very simple. Yes, the main idea, we know that we use a lot a statistical approach to turbulence. So usually when we have a very high dimensional system, we are not interested so much in one particular event or one particular trajectory in the phase space, but we want to know about the probability of some events taking place. So in a way, it is convenient to have tools that are oriented to that, to just understanding what is happening with the probability distribution, either if we do modeling or control. So that's something that is useful. And in some cases, another topic that is interesting for me is related to how to analyze the cause and effect between those events. It is also useful to have tools for that, and tools that are, again, oriented, or they rely on the probability distribution of the events. And in the last case, it's even rare to have those tools in turbulence research. So when what I found, and I got interested on this, is that you can actually use the framework of information theory. It's just a way of working with this probability distribution. So that's why I wanted to look into that. And that's what I'm going to show here, the goal. So information theory is a science of message communication. It was mostly introduced by Shannon. And what you will see here is a way of working with the probability distribution of events. That is very convenient because it allows you to prove some theorems and to have some tools that can help to understand the physics of the flow. So in particular, I want to reformulate the three problems, the one of what is the cause and effect, or the reduced order modeling, and the control for a turbulent flow. So I'll go one by one. I'll show a bit of the theory that is needed, and then I'll show one example. And again, I'll try to keep everything very high level, so it's going to be more an overview. So maybe if someone wants to know more about the details, you can go to the paper and then talk to me later. So let's talk about the first, some definitions that we need. Actually, we just need a few of them. I've been talking about information. I didn't specify exactly what is that. So we are going to be working with a random variable that will have some probability mass distribution, the P. So the information content of one event, so we assume that that variable can take one value, the variable X, is this I here. So it's just the minus the log of the probability. So we can think that in this example of why that is information. So if we have a collection of events, like for example, imagine tossing a fair coin n times. So you will get, for example, head, tails, and you keep going. So the probability of that happening, what we have to do is to multiply the probabilities, but instead of that's a multiplicative process. So we can transform that into an additive process by taking the log. So that's what we do. And when we do that, actually, we are talking about the amount of information that we need to actually encode that variable. For example, when I flip the coin n times, I will need n bits if the coin is fair. That makes sense in a way, but this would be one event. So in general, we don't care about one event, we care about the average, what is happening on average, and that's what is called the Shannon information. Is just take the expectation of that information just by multiplying by the probability of each event that's always larger than 0. And that's the average amount of information. So this is the quantity that I'll be using. And it literally means that. It means that if there is a variable X and I tell you that the variable is 3 megabytes, it literally means that you will need to give me a file with 3 megabytes to really specify that variable. So that will be on average the size of the file that you need to give me. So if I really want to know the value of X, that is also somehow intuitive. So we are going to be working with that. We need two more definitions. One is the information, the Shannon information that is conditioned to another variable. So this, I'm going to use this notation like is the h of x conditioned to another variable y, and the interpretation of this is that is useful is the uncertainty. So if I know a variable x and I condition to y, I can understand this as what is the uncertainty, meaning how many unknown bits in the state x after knowing the state y. So I will use also this interpretation. And the last definition is the mutual information between two variables. So it's just the overlap. If we have two variables, we can compute also the overlap of information between them. And that's what is called the mutual information. In this schematic here, you see the relationship between the different ones, like the conditional and then the mutual for two variables that they can overlap in the information content. Okay, so this is what I'm going to be using. This is what we need. And let's start with the first problem, the causality. So the way I'm going to define the causality from this information theory point of view is as the information flux between the variables of interest that I have in my dynamical system. So that's going to be my working definition. So let's consider then set up the problem. So imagine that I have a dynamical system, for example, the Navier-Stokes equations, and I discretize the system in space and time, and then I get this equation that Q is the state vector, so these are the velocities and the pressure, and F is just a map that is going to advance the solution in time. So now consider this case. You consider that I decide to divide my phase space Q into two components. One I'm calling Q sub I, and the other one is crossing that I, but altogether is the full phase space. So it could be an arbitrary separation of the degrees of freedom that I have. So what we did and what you can prove is that you can show that the information that you have in the future. So if I consider one of these components, Qj, one of them, so it could be, for example, the velocity in a given point, location, you can show that the information of that in the future is equal to the sum of all the information coming from the past. This happens because this is a deterministic system. So when you set the initial condition, then you know what is going to be the future. So if you translate that into information theory, it means that you have some past states at time n, and we are going to find some fluxes t from some variables to j, and all that together will give me the information in the future of that variable. And you can actually derive what is the particular formula that you get. I'm not going to emphasize so much the formula. The idea is that all the information of a variable in the future is coming from the past. And this is what we can use as the definition of causality. These fluxes, we can use them as a quantification of how important is one variable to the future of another variable. And there is this interpretation, so the interpretation of this T. So this T is going to be the causality from this I, and I could be one variable or a collection of variables to another variable J in the future. So we can interpret this as how much the past information in this collection of variables, Q sub I at the past, time n, improves our knowledge of the future state in the time n+1 of the variable J. So this is a way that is non-intrusive in the sense that we don't need to modify the system to see what is happening. And we just need to post-process some data. And this will give us a feeling of how much information is transferred from one variable to another in the future. And we can use that as a quantification of how important is one variable to the future. It literally means that if we get the knowledge of this variable in the past, then we will be able to reconstruct in a way, if you want, this other variable in the future. So now you can also think of causality in a different way, like introducing an intervention in your system, like a perturbation, and then see what happens. That's actually also connected to this in a particular way, but I'm not going to discuss that in this talk. So let me show you an example of one of the applications that we did. In this case, we took the definition of the information flux, and we wanted to study the energy cascade, how the energy propagates across different scales. So we took DNS data. What you see here is a region of energy transfer. This is Reynolds lambda 380. And this database is coming from Jimenez. It was generated by Cardesa. So it's a time-resolved data set. But you know, if we take the equation for the kinetic energy, the filter velocity, we get this equation, and there is this term that is the interscale energy transfer. So this will tell you how the energy is going to be transferred across scales. So we took this data and computed this interscale energy transfer. And then we decided to do this. So this equation is for one filter width. So we did this for 4 different filter widths, and we got these 4 different energy transfers. So from 1 to 4, this bracket means that we average that value in space. So we get a time signal. So we got 4 time signals that they represent the energy flux at 4 different scales. These are the scales that we use to filter. The delta is the size of the filter. So we go for the largest scales, that's 1, close to 160 eta, to smaller scales, close to 21 eta. Once that we have this set of variables, we can compute how is the information transfer between them, just using the definition that I have shown before. And we can organize all that into this map. So this is a causality map. This is the T that I introduced, the information flux. And the way I'm organizing this is in the horizontal axis is what I call the cause. So this is the variable of origin, the I, and then this is the effect. This is where this cause is going, and the variable J, and here you have the transfers. So this, I didn't use the brackets, but there are these 4 signals here. And then I'm just blocking also the diagonal. That's why it look pinkish, because usually the diagonal is the self-information, like how much information is transferred from one variable to itself. Usually that's the largest component. But in this case, I'm interested in how the energy is transferred between different scales, not just within the same scale. So then that's why this is blocked. But then what you can see here very clearly, like it looks very neat, how the energy is following really a sequential path in a scale. It will start in 1 and go to 2, then to 2 and go to 3, and the 3 and go to 4. And the other values are non-zero, so there is also transfer in this other case. This region here will imply the inverse energy cascade, and here is still like the forward energy cascade, but it's much weaker. So we get these 3 steps. So in a way, this is a case where applying this definition of information flux really shows in a very clear fashion how is this propagation of energy in a scale sequentially. If you try to do something different, for example, use a cross correlation, then this map, you can see that that's done on the paper. It really looks more messy. Like it doesn't look so clear. It's more opaque what is happening. You have a lot of transfer. Everything is very strong, but here is very clear what is strong. So this is a clear example. I think that there are other examples that are cited on the paper of how you can use this to try to maybe understand a bit more about the physics. The second case that I want to talk about is about modeling. And in this case, when we reframe the problem of modeling, you can think of the main goal of modeling is to preserve the maximum amount of useful information from the original system. So you can also think that modeling is a problem of information. So you remove degrees of freedom and you are losing the information from those degrees of freedom. So let's pose the problem now in that way. This is the same starting point as before. This is our discrete map for Navier-Stokes, and we have our degrees of freedom from 1 to n, the state vector. So now what we are going to do is, again, partition. We are going to do a truncation of the system. So we are going to partition the phase space into 2 components. The Q tilde is the degrees of freedom that I want to model. So this is going to be information that I can access. And the Q prime are the degrees of freedom that are going to be lost. So this is information that I cannot get anymore. So this is going to be lost forever. So if we do this, that this is just thinking about I'm truncating degrees of freedom, that at the end, that's what you are doing when you are modeling. What we want to do with a model, and the model is called HAT because it's an approximation now. This is my equation for the model. I want to model these degrees of freedom. So the way I'm posing this, imagine that I want to, from the initial condition, the initial system that is truncated, I want to advance to the future and get a solution of that. So what we want to get with a model, we want to predict the future state with some given accuracy. Let's say the accuracy is epsilon. So this difference between where I predicted and the exact value that I should get, I want this to be less than some threshold in the error. So what we show when connecting this is that you can find a lower bound of how good your model can do that is related exactly to how much information you lose. So you can show here, this is the full formula there that I'm not going to explain all the terms. I want to focus on two things here. So what you see here on the left is the amount of, is the average error, the expectation of the error. And then that's going to be proportional to the amount of information that you want to model. So as you want to model more amount of information, obviously the error, they tend to go up. And the second term has to do with the amount of information that is preserved from the original system. So that's why it appears this mutual information between what you got and what you should get. So this equation is not telling you exactly how to build a model. So if you want to now have a model for your problem, you need to understand your problem. But what this equation is telling you is that whatever you do, there's going to be always a lower bound. And that, I mean, you cannot do better than this. So it doesn't matter what you do with your model. Once that you set your model, your variables, then this you cannot go below. On average, you cannot go below this lower bound. So in a way, it can help devising new models. So then we also took this and did an example, and the example is a follow-up of the previous case. So the example is we again have an isotropic turbulence case, the same case as I was showing before, and now we want to do a large-eddy simulation using 64 cube points. Before, the previous case was 1,000 cube. And I want to use a subgrid-scale model. So this is just a generic form of a subgrid-scale model that depends on rate of strain and also this rate of rotation and rate of strain. And I'm highlighting in red here the two parameters of the problem. So I have theta1 and theta2. Those are the ones that I want to find. And so the modeling assumption that we used in this example to obtain these model parameters is based on, is inspired in a way in the equation that we got before for the modeling error. We want that lower bound to be very low. And we show that one way of doing that is to impose this condition that the information content of this variable gamma on a scale 2 delta has to match the information content at a lower scale, rescale by a factor. And this gamma is just the energy transfer plus the dissipation of the molecular viscosity and the dissipation of the eddy viscosity. I want to show that these two are equal, and we also show that this actually is also equal to the DNS case. So this model is just, we impose this condition, and this condition is the one that we use to get these two coefficients. And then we run the case. This is what we got. What I'm showing here is the prediction that we got for the kinetic energy spectra. There are 4 cases here. The dashed line is a DNS. The red line is the actual model that here we are calling information preserving subgrid-scale model. The dash is no model, this dotted line. So you see that you get this pile up of energy. And the blue I'm calling here optimal is just that we did a parametric sweep of all these values to get what is the best we can do. So the blue is really the best you can do. But that's obviously so with some tuning. In the other case of the red model, the red line, there is no tuning. It's only based on this condition. So this also shows that you can use the concept of information in a way to obtain models that they perform well. This model is essentially the one that we got. It's similar in a way to dynamic Smagorinsky when you look at the errors, but I want to emphasize that the principle that is based on is very different. So it's based on conserving the amount of information between 2 different scales. So in that way, the approach is different from the typical cases of eddy viscosity models. So you can read more about this example, but again, connecting to the previous equation, you can see that there are limits of how good your model can do related with the amount of information that is preserved and how your model is able to preserve that information. So the last case that it will take me 5 minutes to talk about is the case of control. So we can also think of the task of optimal controls. We can pose that task as the reduction in uncertainty of the control state given the information collected by the sensors and the action performed by the actuators. So we can think that what we want to do with the control is we are going to be measuring things in the flow and acting on the flow. And our goal is to be 100% sure of what is going to happen in the future. So if we are able to do that, then we are able to control the flow Obviously, that's not going to be possible in general, but that's what the control should aim to do. So if we pose the problem, I follow the same notation as before, the evolution for a dynamical system under actuation. The first equation is the same equation I've been describing up to now, but now there is a small modification that is, there is this A, and this A is the actuation. So now I have another equation for the actuation, and the actuation A depends on S, and S is, there's another equation is the sensor, and the sensor depends on the state at the present end. And then there is J. J is the quantity that I want to optimize. So usually I don't want to optimize the full state Q. I just want a subset, for example, the skin friction. And that's a function of my state vector. And the actuator and the sensor, you see here, these thetas, they are the control parameters. So this is what I want to find. So going back to the concept of information, we can define observability and controllability. In this case, the observability is given by a mutual information between what I want to control and my sensor, normalized by the total information on the state that I want to control. So this interpretation of this is going to give me the uncertainty in my objective function given the information from the sensor. So this quantity, you can show it goes from 0 to 1. So 0, you cannot observe anything, or 1 is a perfect observability. The controllability is similar. The difference is that you look at the objective quantity in the future, and the information that is shared between that and your actuator, and again, normalized by the total information. So this value can go between 0 and 1. So this can be interpreted as the uncertainty in the target state Jn+1, knowing the present information from the control. So we want to know if we are acting, if we are sure of what is going to happen in the future. So with this, the last piece that we need of the theory is how we define the task of optimal control. And the way we introduced that was posing the problem as a reduction in uncertainty of the control state. That is the statement that I mentioned at the very beginning, given the information collected by sensors and actuators. So again, to emphasize that, I have imagine this green distribution. So this is the control state. This is the probability distribution with some mean and some standard deviation. And what I would like to have is not this. What I would like to have is this other distribution here, that because I like to have this mean and then this standard deviation. So I have some targeted mean and variance that I want to get. So the idea is that I want to have a lot of certainty that I want to get this, meaning that I have a lot of information about what is going to happen in the future. So you can just rewrite this statement that I have here on the top in terms of the information-theoretic quantities. So the optimal control parameters, they can be done by optimizing these quantities. So the first term is a cross-Shannon information between the future state and a rescale state, that is just taking the state that I have and rescale it to the position that I want. And then the last piece is the entropy that I have in the future state. And yeah, by optimizing this, you will be able to control the PDF. So in this case, we don't control one mean quantity in particular. What we are trying to control is the PDF. In this case, 2 moments of the PDF, but we can control all the moments that I want. We can even control the full PDF and try to define that. So let me show
5
you.
minutes.
Yeah, I'm almost done. So this is the example that we did. We apply this to opposition control in a channel flow. So there's a small box and a small Reynolds number. Now, you know about opposition control, we want to reduce the drag. We have a sensor that is the plane where we get some vertical velocity and we apply that at the wall, and that's the actuator. And what we want to do, the target state that I will ideally like to have is 0 drag. I don't want to have drag and very, very low fluctuations of the drag. This is not how arbitrary, this is what I would like to have. So we apply just the minimization that I shown before, and this is what you get. We have the uncontrolled case, so this is the probability distribution of the stress at the wall. The uncontrolled case is this kind of cyan. Then we apply the optimal control that we were able to shift the drag to lower values. And the dash is what this ideal state that we would like to have. We would like to have this PDF like 0 drag. Obviously, that's not possible, but the optimization is going to push our solution in that direction as much as possible. The optimal control that we got was that the sensing plane has to be y plus 13, close to 14. And the amplitude of the blowing and suction has to be close to 1. This is compared to the velocity that we measured. This is 20% reduction. All this was known. This is consistent with previous works by Choi. We just wanted to make sure that this approach can also be used and is meaningful when we do control of a real case, more realistic case like a full turbulent flow. So you can see here that you can do that. The main difference with other methods is that now we can also control the shape of the PDF. So our method will also try to do that. So with that, that's the three cases that I want to discuss: theory and examples. And I put like a summary here of each of them. So in summary, what we found is that it seems to be convenient for many problems to formulate them using the information, because it gives you some theorems that you can rely on. And also it gives you a way of working with probability distributions that is very natural. So that was we tried to use for these different three cases. And you have the definitions here of how we reframe these cases in information-theoretic terms. And again, you can refer to this manuscript here if you want to look at more details. And yeah, thank you for your attention.
Yep. Questions? Paolo Lucchini.
So I've always been a big fan of information theory, but a big weak point of it is estimation from an empirical sample. Could you tell something more about how you estimate the Shannon entropy and even worse, the mutual information, and how are you binning the velocity and how much reliability you attach to your estimation? Some details on this.
Yeah, so if I go back to, let's go to the definitions where I have the quantities that I want to estimate here. So when I want to estimate the Shannon information, what I need to do always is to get a probability distribution of whatever quantities I want to estimate. So that might be, depending on how many variables you have, it might be trivial because we have a lot of DNS data. Or in some cases, it might be very challenging if the PDF is very high dimensional. The way we do it, we use the method of the kernel approximation method. So we need to do approximations of reconstruct locally how the PDF is going to look and make some estimation of the Shannon entropy, or well, the Shannon information. In that case, also that doesn't need to be the probability of the velocities in particular, could be the probability of any variable that you want. But you have to use like a way of reconstructing the PDF, and usually we use a kernel method. Still, you are always limited by the amount of data that you have and by the dimension of the probability that you want. If you want to estimate a probability that is very high order, many dimensions, that's probably going to be a challenge.
Okay, is there any other question? I do have a question. I'm going to follow in this, with Paolo's question. You have to be binning your information somehow, your variable somehow, to compute an entropy. And then you have several variables. Is there any effect of binning differently one variable from the other variable? Is it possible that you bin one much better than the other that biases your gross entropy?
Yeah, so that's also sensitivity that you have to assess. Actually, what you say actually could happen very easily. That depending on the binning that you use, then the particular amount of Shannon information that you get changes, and it changes. It has to change in a way depending on how you bin your system. The question is that relevant for what you are trying to look at, or are you binding fine enough so that doesn't matter anymore? But not super fine, because this has to be still a discrete system. But that's also an important sensitivity, that is related to the technical part of how to estimate the Shannon entropy. All at the same time, there is like a full industry of people working on tools to do that. So, but still, it's important to be aware of that, of the how you're doing the binning, and check that whatever you get is independent of the particular binning that you have.
I'm thinking basically on your example on the cascade, where you had two variables that were two two velocities or to whatever at two different scales.
Yeah.
There, I mean, how do you choose the relation of the binning in one scale with the binning in the other scale? And might that dark square there might have something to do with the way you bin?
Yeah, I try to make sure that that's not the case by changing the binning. And the way I do the binning, we use the binning to compute a PDF. So that's one way of computing a PDF. But we use a kernel estimation method. It's not based on binning anything. It's based on locally reconstructing what should be the shape of the PDF with the information that you have, the data points that you have. And there are a few other methods to reconstruct PDFs, like at least there are 4 different types. So we use the 4 of them. We plot them up using the 4 of them. We also make sure of the amount of data using all the data we have, and then see that the pattern that we see in the map remains and is the same. So we always try to do that. Although it's true that depending on the method you use, you will see some sensitivities on the actual values that you get. But at least we try to make sure that the takeaway, the conclusion, that remains the same. In this case, we check that, so it remains the same.
Okay, there's a question from the net, I think.
I had a question. So how much does this is a very interesting talk, by the way, but how much does your framework change if the model is stochastic?
So if the model is stochastic, you have to introduce a few changes, and I come back here to the very beginning. So many of the theorems that we derive, they assume that the system is deterministic and is closed. So when that's the case, you can show that the information can only be conserved or can only decrease in time. If you now have an stochastic term, that's a source of information. Now information can do anything. It doesn't need to be conserved or decaying. The information of your system can also go up. And that will imply some modification. You can still derive some of the theorems that we have. All of them you cannot in that case. But we actually did that in the case of control. And although I didn't talk about that, in the case of control, what we did, if I go to the equations that we have, we changed the first equation, that is the state of the system, and we added a noise, a stochastic term. And then you can show that that will affect how much the sensor and the actuation, how effective they can be because of that noise. So that can be included. We didn't do it for the other 2 cases, but we did it for the control.
I think
that will affect that.
And the reason I ask is because your late MIT colleague, Ed Lorenz, had this idea, which I think has gained more and more support, that the Navier-Stokes is actually not deterministic. In fact, it acts essentially as a random system. So that if you add even the tiniest noise, and this could even be molecular noise at the smallest scale, that it becomes essentially unpredictable and acts just like a random system. So in fact, I think that the Navier-Stokes equations is better understood as not a deterministic chaotic system, but as a random system.
Yeah, that's actually, I agree with that. That's a good point. And the way we decided to, because we are looking, usually the work that I do is more related to very large scale macroscopic quantities that maybe are not so much affected by small fluctuations that you might have. That's why we decided to formulate it in this way.
Well, according to Lorenz's idea, if you look at any scale of motion in 1 eddy turnover time of that scale, the molecular noise will appear. So in other words, it will propagate up to the largest scale in 1 eddy turnover time of whatever.
We really have to move to the next talk. Thank you.
Yeah, okay, sorry.
Well, thank you, Adrian. I mean, thank you again. Okay, so the next talk is going to be by Koji Fukagata, who I hope is there.